Okay, so what is the last thing that we put on a problem when we integrate? What's the very last thing we always write on? Every single problem we find the antiderivative. Plus C, cool. So there's a lot of times where if you're given enough information, you can actually find the exact value of C. Okay? And we call these initial value problems because you're given an initial function value, and you can use that to find that constant. Okay? So if we're given the derivative of a function and a point on the original function, so that could be f of 3 equals 7, or if you're given a coordinate, any type of thing that gives us an x value and a y value, we can evaluate for C. So the process is a two-step process. We integrate just like normal, put plus C at the end. We plug in or substitute in the x value and set it equal to the y value, and we solve for C. Okay? Let's do a couple of, or we'll do one example, and then we'll do a little more complex problem. So it says find f of x when f prime of x equals secant squared of x. And we're given this initial value. F of pi over 6 is 12. So first off, f of x is the integral of f prime. So it's secant squared x dx. Now remember, the integral symbol and the dx go together whenever we write the notations. We want to make sure we put those both. And so what is the integral of secant squared x? Say it loud. Tangent x. So tan x plus c. Okay. Now again, we're given an x value and a y value. So we want to find f of pi over 6. We do that by plugging in pi over 6 to our function. So tangent of pi over 6 plus c. Okay. Now what is tangent of pi over 6? Square root of 3 over 3. So that plus c must equal what? Must equal 12. All right, so we plug in our x value. We set it equal to our y value. Okay. And so, well, this means that c must equal 12 minus the square root of 3 over 3. Okay. Now, the original question, though, said find f of x. So we're not looking just for c. I mean, c is necessary, but our actual answer will be f of x, which we already found everything except for c. So we have tangent of x plus c, which was 12 minus the square root of 3 over 3. So what we're really doing here is we're doing calculus first in the integration, and we just an algebra to solve for c. Okay, so we're not adding on a whole lot here. We're just able to find that initial constant. Now, if we're given the second derivative of a function and 2 points, it's possible to find the constant. Okay? And this is a little bit longer process because, well, if we have the second derivative, if we integrate once, what do we get? We have the second derivative, and we integrate once, what do we get? The first derivative. So to get the function, what do we have to do? Integrate again, right? So it's not, we don't call it the second integral, we just say we repeatedly integrate. Okay? Now, if you think about it, the first time we integrate, we're going to get a plus c at the end. Right? And then when we integrate again, well, the integral of that constant will be that constant times x. So that has to factor in there someplace. There's two possibilities. In one case, you're actually given f prime of x. So you're told the derivative is 4 when x equals 2, or something like that. So at that point, if we're given an actual value for the derivative, when we integrate the first time, we can go ahead and solve for c right then and there and get a number, and then integrate that with the number in there. If you're not, then you have to be given, if you're not given a value for the derivative, then you must be given 2 points on f of x, in which case we'll actually leave c, we'll integrate with c in there, pretend it's just a constant, and then solve for both at the end. Okay, so we're going to do 2 examples. Papers are right there. 2 examples. One, so notice in the first example here, we have the second derivative, right? We get an f double prime. We're also given a value for the first derivative when x is 2, right here. And then we're given a function value when x is 1. Now, it's not necessary that we have consistent x values. That doesn't have to be, just like in this example, it's not. Okay, so it doesn't really matter if we have consistent x values. It doesn't factor into what we're doing. Okay? So let's start off. We have the second derivative, so if we integrate once, what are we going to have? Okay, so we'll have f prime of x, which would be the integral of x cubed minus x squared dx. Now, f prime of x then, well, the integral of x cubed would be x to the fourth over 4. The integral of x squared would be x cubed over 3. Let's see. Now, again, we're told f prime of 2 is negative 1. So let's find f prime of 2. F prime of 2 would be 2 to the fourth over 4 minus 2 cubed over 3 plus c. Now, what does f prime of 2 have to equal? It needs to equal negative 1. So we have 2 to the fourth, which is 16, divided by 4 is 4, minus 2 cubed is 8 over 3 plus c equals minus 1. Now, common denominator here, well, this would be like 12 thirds, right? And this would be like 3 thirds. So I've got 12 thirds minus 8 thirds. So that's 4 thirds plus c equals negative 3 thirds. And so we subtract 4 thirds. So our c here must be negative 7 thirds. So that means f prime of x, which notice we found right here, with everything except for the c, which we now have, is x to the fourth over 4 minus x cubed over 3 minus 7 thirds. This was actually solves for c. There's no more c here. But we're actually looking for f of x. So we have to integrate our derivative. So the integral, so let me write f of x equals. So f of x now is equal to the integral of x to the fourth over 4 minus x cubed over 3 minus 7 thirds dx. Okay, so we add 1 to the exponent, so our new exponent would be the fifth power, and we divide by that exponent. Now keep in mind, when we divide by 5, we already have a fourth, right? We're already dividing by 4. So if we divide by 5, we multiply those two numbers. So we get x to the fifth over 20 minus x to the fourth, and 4 times 3 gives us 12 minus 7 thirds x plus c. Again, at this point, we're actually given f of 1 equals 3. So we want f of 1, which would be 1/20th minus 1/12th minus 7 thirds plus c. And that needs to equal 3. That's the given information. That's the initial value. Now, the purpose of this is not to be able to combine like terms with fractions and stuff. It's good practice, but don't let that be your stopping point. Okay? So feel free to use a calculator, but it's good practice anyway. So what would be the common denominator right here between our 3 fractions? Well, it has to be some multiple of 20, right? It's the biggest one. So that 40. 3 doesn't go into 40, so 60. If 12 goes into 65 times, and 3 goes in. So these are 60s. So we'd have 3 60ths, right? And we would have 5 60ths. And then we would have 20 times 7, which is 140. Right? And then 60, we have 1s here, so we have to multiply by 60, so we have 180. So we've got 3 60ths minus 5 60ths. That'd be negative 2 60ths. Minus another 140, so a negative 142 60ths. So negative 142 over 60 plus c equals 180 over 60. So now if I get everything in terms of 60, so that way I can just add whole numbers. I don't like messing with fractions, but I don't have to. So I add 142 to both sides, and so this results in C must be, well, let's see here, 322 over 60. And I think we can probably cut them both in half at least. So we get 161 over 30. Okay. So again, we're looking for f of x, right? Not just c. We're actually going to write our whole function. So now that we found that c, we can write our whole function. So f of x is equal to, now remember, x to the fifth over 20 can also be written as 1/20th x to the fifth. Right, so I could write x to the fifth over 120 as 1 over 20 x to the fifth. Either way, it doesn't matter how you write it. You just need to be able to see them as the same thing. So minus x to the fourth over 12 minus 7/3 x plus 161 over 30. Notice how the fractions get a little unwieldy? That's just because of the nature of integrals, where we have to add one to the exponent and divide. You're liable to get some interesting fractions. But also keep in mind, usually the problems are written to work out, or they're written to be complex like this. The person who comes up with the problem will usually make it a certain way. They're trying to focus on something. So in this case, the example is written so that you see that you don't always get really nice numbers. Sometimes you will. Sometimes you won't. So you got to be able to, it's okay. Sometimes nice numbers don't come out. Now look at the next example. Again, we're given the second derivative, right? We're asked to find f of x, but this time we're not given a value for the first derivative. We're just given two function values. Okay, so keep that in mind. So we start off, if we integrate once, what do we get? If we have the same derivative, we integrate, what do we have? First derivative, so f prime of x equals the integral of x. You got it? And so f prime of x would be x cubed over 3, or 1/3 x cubed, however you want to look at it, minus x squared over 2, or 1/2 x squared, plus c. Now, we don't have anything, we have no information about the derivative here. So I can't solve for c right now. Okay? So I'm just going to take ahead a step. I'm going to have to integrate this. And when I integrate, I'm going to get another c. Right? Is it going to be the same constant here? Is it going to be the same number? Is it important that we differentiate between the two? Like if I integrate c, what am I going to get? I'm going to get cx. That's why in the practice problems you have to see that as a constant. So the integral of a constant is just that times x. So I'm going to differentiate. I'm going to call that c1. I'm going to keep track of my c's here. Because unlike when we're solving, we have multiple c's at the same step. Like we integrate here, we integrate x squared, we have x cubed over 3 plus c, x squared over 2 plus c. We say, oh, it's just one c. Well, in this case, we're integrating again, and we're going to end up with a completely separate constant. So when we integrate, we get f of x. We're going to integrate x cubed over 3 minus x squared over 2 plus c1. F of x equals. Okay, so x cubed over 3 become, the integral of that will be x to the 4th over 12 minus x cubed, and then we're already divided by 2, so we divide by 3 more, we're dividing by 6, plus the integral of c1 will be c1x, plus, now we need another constant, so I'm just going to call it c2. Now let's see here. We are given f of 1, right? Let's find f of 1. Well, 1 to the 4th power is 1 divided by 12 minus 1 to the 3rd is 1 divided by 6 plus C1 times 1 is C1 plus C2. And all of this is going to need to equal -3. Right? That's the given information. Now we're also given f of 0. So if we plug in 0, 0 to the fourth is 0, 0 cubed is 0, C1 times 0 is 0, so we're just left with C2. And that needs to equal 4. Notice now we have kind of actually a fairly rudimentary system of equations. We actually know that C2 is equal to 4, so we can take that and plug it in, and then solve for C1. Okay. If we had C1 in here, we'd have to do some type of solving and use one of your methods for system of equations to solve this equation. So let's see here. We have 1/12 minus 1/6 plus the C1, which is what we're looking for, plus 4 equals -3. So common denominator I see here is 12. So I've got 12 as my biggest. So I'd have 2/12. 4 times 12 is 48, so 48/12. And then -3 would give me -36/12. So 1/12 minus 2/12 is -1. Plus 48 gives me 47/12. Plus C1 equals -36/12. So then I subtract 47 from both sides, so C1 would be -83/12. So we already knew C2. Just solve for C1. And we have our function right here that all we need is C1 and C2. So we write our final answer. F of x equals 1/12 x to the 4th minus 1/6 x cubed plus what times x? -83/12. So I'm going to change that plus to a minus. Minus 83/12 x. And what's the last term? Plus 4. Okay. What questions we have over these 3 examples? What is new here? What would be finding the answer? Okay, so some of them, yeah, we're starting off with the second derivative. That's new. That wasn't on the last stuff, right? First time you're saying integrating twice in a row. Okay. What else? And you were saying finding the C, right? So actually having to do algebra after you think you're done, right? So after calculus, then we have to do some algebra before we write our final answer. Okay. So not a whole lot new here per se. That's why on the title page it says an application of the integral. So here's another application of the integral. Kevin, would you read nice and loud for us?
In physics, when given a position function of time s is t, the velocity function vt is produced by taking the derivative. The acceleration function a of t is produced by taking the derivative of the velocity. Likewise, beginning with the acceleration function, integrate twice to produce v of t and s of t respectively.
Thank you. So this little table here with the arrows is actually pretty good. Believe it or not, when you take engineering physics in college, you'll really appreciate this concept. If you can just get this down now, it'll make your life in physics easier. Because what you're really doing is, if you know a position function, the derivative is the velocity, the second derivative is acceleration. If you know acceleration, to get to velocity, you integrate. Given velocity to position, you integrate. So there's this direct relationship between the derivative and the integral. Okay? So all you have to remember is what goes to what. So the derivative of velocity gives us acceleration. That's what you need to remember. Okay? And the units are really helpful for remembering this. So if you think about position in meters, okay, the derivative is a rate of change. So the derivative gives us a meters per second unit. And then if we differentiate again, when we multiply, essentially think of it as doing per second per second. The second derivative gives meters per second squared. Okay? To integrate, you get rid of one exponent on the denominator in a way, right? And so there's a direct connection between the units and the derivatives. In fact, this for a lot of people, I know for me personally, whenever I took physics, I was very confused for a long time until this suddenly clicked. And then calculus made sense to me. I was already in Cal 3. And calculus suddenly made sense because I went, oh, that's all it is. It suddenly clicked, and that's what we were doing. This was never made, for whatever reason, didn't click. So I could do calculus really well. I didn't make the connection of what I was actually doing. And so when I took physics, my first semester of physics was pretty tough because I hadn't made this connection. So when we're doing all these formulas, I'm trying to memorize everything as opposed to saying, okay, give me a position, I can find the derivative, which is usually pretty easy. So, and in fact, if you open up your physics books and you look at the general position function for a falling object, take the derivative of it, you'll see the velocity of a falling object. You take the derivative, you see your constant of negative 9.8 meters per second squared. So there's a direct connection. All right. So an object is moving along a straight line with velocity given by v of t equals that function. Find both acceleration and position when the object is at s equals 5 when t equals 2. So it's asking us to find acceleration and position. So we're finding two things. So we need to think about what is the relationship between what we're given and like acceleration. So how do we go from velocity to acceleration? Okay, so we look back at the table, and acceleration is the derivative of velocity. It's the rate of change of velocity. So what's the derivative of 3t squared minus 6t? T minus 6. So there's our acceleration function. It's easy. Now we're given a velocity function and we want a position function. So how is position related to velocity? So we're given velocity, right? To get to acceleration, we had to find the derivative. Given velocity, how do we get to position? We integrate. Okay? So s of t will be the integral of v of t, dt. That will be the integral of 3t squared minus 6t plus 1 dt. So let's see, the integral of 3t squared of t cubed over 3 minus integral of 6t is 6t squared over 2 plus the integral of 1 is t plus c. Now what is the initial, I'll call it the initial condition here. What's the initial bit of information we're given? Okay, so this part right here. All right, so how would I write that in function notation in terms of position? S of what? Equals what? Is it S of 5 equals 2, or is it S of 2 equals 5? That's an important thought process. So inside of here is our time, so S of 2 is 5. So we're plugging in 2 and setting it equal to 5. Did I make a mistake? Thank you. Okay. And so notice we can also simplify this, right? So we can write S of t is equal to t cubed minus 3t squared plus t plus c. And we can check our answer really easily by finding the derivative of each of these terms just to make sure that it jives with this. In fact, anytime you can do that, anytime your integral is a polynomial that's easily, where you can just do the power rule really easily in your head, do it. You will catch more mistakes than you'll ever believe by doing that. Because it's really easy, especially once you get the hang of this and you're doing 20 or 30 problems and it's just second nature and you almost have to, you don't have to think a whole lot because you're doing the same thing. You'll be surprised how often you'll accidentally divide by 3 instead of by 2. Even though you have a 2 written, you divide by 3 and you write a 2 right here. Right? You probably found yourself making mistakes like that just in general, right? But whenever you go to find the derivative, you'll catch it because you'll say, oh, the derivative would be 3t squared, okay. And to get a 2, you get a 4t. Oh, wait, something's wrong, right? It's really easy to catch mistakes if you just do the mental math and say, okay, derivative of t cubed is 3t squared. Derivative of 3t squared is 6t. Derivative of t is 1. Good. They're right. If it's something that's really, funky fractions or something, maybe it's not worth your time every single problem. But if it's easy like this to check your answer, you should every single time, because it won't take you very long, and it's worth the effort. So now we want to find s of what? 2. So 2 cubed minus 3 times 2 squared plus 2 plus c is equal to 5. 8 minus 12 plus 2 plus c equals 5. Now you got to, if you're doing this without a calculator, guys, which you should be able to, but you've got to be really careful here, because most of you, how do you, somebody tell me how you remember order of operations. What's the acronym? You learned PEMDAS, right? Why? What does PEMDAS stand for? Somebody help me out.
Parentheses, exponent, multiplication, division.
Okay. So what comes first, addition or subtraction?
Addition.
It's whichever one comes first from left to right. So PEMDAS is wrong. It's a horrible way to remember it, unless you remember, but multiplication division isn't really just ND. It could also be DM. It's not just AS. It could be SA. Okay, so PEMDAS could be PEDMAS, it could be PEDMSA. All kinds of ways to write it. So you got to be careful, because notice what would happen if you did addition first here. You would add the 2 and the 12 and get 14, and then 8 minus 14 gives you negative 6. Whereas 8 minus 12 gives you negative 4, plus 2 gives us negative 2. It makes a difference. The correct thing here is negative 2 plus c equals 5. And so c is equal to 7. Somebody did that, right? Or in your mind, your eyes are drawn to the plus. You do that first, because that's the easy one. Subtraction with negatives is harder, requires a bit more thinking. So you're drawn to those easy parts, right? So keep that in mind. You'd be surprised how many times I've seen that mistake made. Okay. So our final answer, our position function, s of t equals t cubed minus 3t squared plus t plus 7. What's wrong? Oh. Well, no, that's just it. They taught you how to do it, and I bet it came up at the time, but it didn't. It just didn't stick. And it's never been an issue, because how often does that really show up and you don't have the calculator to type it in? Right? The reason that it became that we have to have order of operations is because calculators are a fairly new addition to what we do. So, okay, questions or concerns about this? Not about order of operations. About calculus.
No, that's not good.
Huh? That was just a side note of a common mistake that I see, and I put no, and people are like, why did you say that's wrong? Okay, so there are 5 problems. That's it, 5 problems on this, because as you see, they're a little bit longer than the average problem. Okay, so 5 problems to these. This is the last section in this unit on antiderivatives. This is it. This is integrals right here. Okay. Now we're going to do applications, and there's more coming, but this is almost as complex as it gets. It doesn't get too much more difficult than what we've already done. Okay? Which means if you really get this stuff down by doing all this practice, you'll pretty much be set for the semester, believe it or not. So what's coming up really isn't any more complex than this at all. But we will have a review tomorrow and a test on Wednesday. Okay? Over integrals. Just this unit 9. Okay? Look at the assignment.
Well, they haven't done the first one.
Yeah, so trig is open game for sure.